this is how
Okay, everybody shut up now. This is my time to shine. We're going to do a one-day tour of unit conversion, scientific notation, that kind of stuff. So I know a lot of you have done a lot of chemistry and biology, so you've done a lot of this stuff before, but we're gonna go over this. So if you have ways that work for you, feel free to use those. You don't have to use the stuff that I'm going to tell you for this, but I'm going to tell you some ways that work. So if you're you don't have a way that you're used to doing this, then this is an option for you. So first, the idea of units. So every measurement has units. And in this class, all of our units are going to be made up of 3 basic unit types. So there are only 3 basic unit types, but you can use multiples of these to build up other units like meters per second, miles per hour, stuff like that. The first one is units of length. And so those include, millimeters, feet, yards, meters, miles, so on. And while we're here in a physics class, I'll just mention that, light years come up in science fiction or whatever all the time. A light year is a measurement of a length. A lot of people think, it's a time because it has years in it, but it's the total distance that light would travel in a year. So something moving the speed of light, how far it goes in a year, which is obviously a very long distance. The second basic unit type is time. And so this would be like milliseconds, seconds, minutes, hours, days. Years, so on. And then the last one is mass. And the units of mass are, some units of mass are grams. There's one called a slug. That's the unit of mass for British units, imperial units, kilograms. Bathroom scales usually have a setting switch where you can switch between measuring in pounds or kilograms, which kind of gets people used to thinking that pounds and kilograms are measuring the same thing, but in fact, they're not. Pounds is a measure of force. So when you're measuring your weight in pounds, you're measuring the force that gravity applies to you. Kilograms is a different thing, and the scale actually can't directly measure kilograms. It can't measure mass. What it can do is, if the people who build it know that you're going to be using it on the surface of the earth, then they can use your mass to figure, use the force applied to figure out your mass. But just remember that pounds and kilograms are different types of units. The SI units are the ones that we're going to use in pretty much everything in this class. Those are, you can think of it as standard international units. That's not what, it's actually French, what the SI stands for, but it is the standard international set of units. And it includes meters for length, seconds for time, and kilograms for mass. So any units in SI units are combinations of these three things. These are not all of the basic units in the world. You can also think of charge, electric charge as a unit. You can think of magnetic field strength as a basic unit, but we're not using any of those. So these are the only ones we're going to see. So the first thing we're going to talk about is converting units. And the idea is that you often want to express a measurement using different units of the same type. So here is sort of a general approach for doing this, and then we'll just get into a bunch of example problems, and I'll give an example problem that you'll have a chance to work on to make sure it's making sense to you. So the first thing is there is always an equality between, an equality that you can write between different units of the same type. So for example, 1 mile is 63,360 inches. Okay. And you can use this equality to come up with conversion factors. And there's always two conversion factors you can come up with from one equality. So if these two things are equal, you know that if you divide something by itself, you get 1. So we can set up ratios of these that are equal to 1, like 1 mile divided by 63,360 inches. Since those are the same thing, you can think of this as 1, and it's also equal to 63,360 inches over 1 mile. Okay. Since these are both equal to 1, you can multiply these to anything without changing its value, its meaning, And so the way we're going to use this is we're going to, first of all, think of a number and a unit as a number multiplied by something. You can treat it just the same way as an algebraic variable, If this is a foot, okay, then 50 feet is 50 times this length, okay? And so what you're going to do for a unit conversion is you're going to start with the given quantity, and you're going to multiply that given quantity by the conversion factor that cancels the unwanted units. Okay, so like for example, if we want to convert 5 miles to inches. We already know what the two possible conversion factors are. We know that it's either going to be 1 mile over 63,360 inches, or we're going to multiply it by 63,360 inches over 1 mile. The unwanted units are the ones that we started with and we're trying to change. Okay, so this is the unwanted unit. So we're going to start with our given quantity, 5 miles. And I'm going to write this as like a big fraction to be clear about what's in the numerator and what's in the denominator. And then I'm going to multiply this by the one of these two conversion factors that cancels the mile. Since the mile of our starting value is in the numerator, we need our conversion factor to have it in the denominator for it to cancel. Okay, so I'm going to write this as 63,360 inches over 1 mile. I said that to think of these units as the number times like an algebraic variable with that name. So this mile cancels with this one. And the units we're left with are inches, which is what we want. And so now we know that all we have to do is multiply and divide out those numbers and it'll give us the value. And so 5 times 63,630 is 316,800 inches. And I'm going to use a little shorthand that I think was given to me in high school or whatever. Instead of writing all the parentheses, I'm just going to separate the things with like vertical slashes, vertical lines. So I'll write this as 5 miles. That stands in for the parentheses. And then I have 63,630 inches over 1 mile. So what that means is the thing with the parentheses above. Anybody have any questions about that? Okay. I'm going to do a couple more examples where now this was with the unit is just one single basic unit. But now we're going to do some other things like, well, what if you have units multiplied or divided? Or what if you have squares or cubes of units? How do you deal with those? So the first one I'm going to do is convert 61 miles per hour to meters per second. Well, 61 miles per hour, first you have to recognize that that's just a common way of writing 61 miles divided by hours. Okay. Anything that's given as per, that's just saying divided by that. And so now this is what we're starting with. Oh, and I pretend I already did this. Here, just use your electric pen to move this down. Just kidding. I know you don't have an electric pen. But we're going to use the fact that 1 mile is equal to 1609.344 meters. And we're going to use the fact that 1 hour is 3,600 seconds. And like on tests, homework or whatever, I mean, I guess with homework, you can get these out of your notes, but on tests, I'll always give you the equality that you need to do these, okay? Okay, so we're gonna start with, I'm gonna start by being clear about what's in the numerator and what's in the denominator. So we got 61 miles divided by hours. And I'm going to first multiply this by a conversion factor that goes from miles to meters. And then second, I'm going to multiply it by a conversion factor that goes from hours to seconds. And you can just do that all in the same line. Okay. So to go from miles to meters, we know that we're either going to have 1 mile over 1609 meters, or we're going to have 1609 meters over 1 mile. We're trying to cancel the miles, which means we want the miles to be in the denominator, so it cancels this one, okay? So I'm going to write 1609.344 meters over 1 mile. Since these are on opposite parts of the fraction, they cancel each other out. And so now we've changed our units to, our length units to meters. And now we just have to change our time units to seconds. So now I'm going to multiply this by either 1 hour over 3,600 seconds or 3,600 seconds over 1 hour. Which of those do we want in order to cancel these hours that are in the denominator? Yep.
1 over 36.
Yeah, we want the hours to be in the numerator for our conversion factor. So we got 1 hour over 3,600 seconds. So this hour cancels this one. And our time units are seconds. And now you can see that the units of this thing are now meters divided by seconds, which is what we want. All you have to do is multiply out and divide out the numbers. So if you go 61 times 1609 divided by 3,600, you get about 27.26 meters per second. Yep.
On that test, if we got like something quite similar, like 27.27, would you still count that?
Yeah. Yeah. So that brings up a couple of things kind of about tests. The first one is, so I'm only grading your tests and stuff based on how you do the problem, you know, like the steps of how you do it. I don't care anything about significant figures, mostly because, I mean, if chemistry people didn't care so much about significant figures, then maybe I'd feel like it was my job to teach you that, but they care so much about it that I feel like I can just ignore it. And so I don't care how you round. You could call this 27.3, 27.267, whatever. I don't care about that. But it also means that you need to show me the steps of how you did a calculation. And if you did the calculation in your head, which I know some people are pretty good at that, you still have to write down what you did in your head so I can follow the thought process, you know? So I've occasionally on the first test gotten tests where people must have just done all their work on a scratch paper. Then they threw that out on the way out of the classroom and just left me answers. Don't do that. Show me a set of equations so I can follow how you did this calculation. It also allows me to give you partial credit, and I give lots of partial credit. So, I mean, if you did this all in your head and got 24, you know, what am I supposed to, I have no idea, you know, whether that's right, whether that's wrong, whether you just rounded off at crazy times. And so most likely that would be close to no points, you know, even if in your head it all made sense. Any other questions about that example? Okay, so now let's do one where we have, so we're going to have a squared unit. So now we want to express 38,640 yards per minute squared in units of meters per second squared. And we're going to use that 1 yard is equal to 3 feet. 1 meter is equal to 3.281 feet. And 1 minute is equal to 60 seconds. Okay, so I'm going to start with my given value, 38,640 yards, divided by minutes squared. And instead of writing it as minutes squared, I'm going to write it as minutes times minutes. And that's what I'm just always going to do when I have a unit that's squared or a unit that's cubed. I'm going to write it out as times, you know. And now my strategy is going to be, I'm first going to go from yards to meters, then I'm going to go from minutes to seconds, and then I'm going to go from minutes to seconds again to cancel that last minute. Okay. And in going from yards to meters, I don't have a direct way, you know, so I'm going to have to do that in 2 steps. I'm going to have to go yards to feet and then feet to meters. And then I'll do the ones with the time. Okay. So first I'm going to go yards to feet, and I'll do that as 3 feet over 1 yard. So I did that in the way that the yards or unwanted units of yards cancel. And now we're at units of feet. And now I want to convert feet to meters. So I'm going to put 3.281 feet down here to cancel with this one, and 1 meter in the numerator. So those feet cancels those feet. And now we have length units of meters, which is our goal. And now we just have to start working on these time units. So we're going to go 1 minute over 60 seconds. And I chose this one because we want to cancel minutes that are in the denominator of the original expression. So one of those minutes cancels this one. But we still have 1 more minute that we have to change. Right now we would have units of meters per minute per second, some, you know, sort of a crazy thing. You could express, I mean, that really, you could get a right answer in those units, just no one uses those units, and those aren't the ones we're looking for, so we're going to keep going. And so I'll go 1 minute over 60 seconds again. So those cancel. You got seconds. And now we have units of meters per second squared, which is what we want. So now just multiply and divide out the numbers that you have, and you get 9.81 meters per second squared. I know some people, this is perfectly fine as a first physics class, but I know some people have taken physics before, like in high school or whatever. Anybody recognize what that is, 9.81 meters per second squared? Yeah. Yeah, that's right. That is the acceleration of any object in free fall as long as there is not significant air resistance. So if air resistance wasn't an issue, if you dropped a marble and an elephant and measured their accelerations downward, they would both be this, okay? Even though their masses are somewhat different. And we'll talk a lot about that. We haven't even talked about what acceleration is, but that's going to be a surprising thing that we're going to spend a bit of time on. The fact that any two things, no matter what their weights are, fall the same if there's no air resistance that's significant. Don't drop elephants, though. That's animal abuse. Okay, so let me give you one to work on to just make sure that you're sort of following how these steps work. Whenever we do these in class like this, feel free to talk to each other out loud, share answers, ask me questions if you get stuck. But it's just a chance for you to sort of solidify this stuff. Okay, so the density of steel is about 7,000 kilograms per meter cubed. And if you're given that 1 meter is 3.281 feet, the question is, what's the density of steel in kilograms per cubic foot? Okay, so what that says is if you had a cubic meter of steel, a meter is maybe like this. So if you had a cube block of steel that was this long, that high, and that deep, it would have a mass of about 7,000 kilograms, which comes out to a weight of about 15,000 pounds. Okay, so take a couple minutes and see if you can work through this. Feel free to work together with people, ask them questions, ask me questions, and then I'll go through it to make sure that we're all on the same. Start with 7,000 kilograms divided by meters times meters times meters. And just, we don't have to mess with the kilograms in this case, but just one by one, we're going to go through the meters and convert those to feet. So I'm going to go 1 meter over 3.281 feet. That cancels the first one. And then do it 2 more times. That cancels the second one. Last time. That cancels the third one. And so now the units that we have are kilograms per feet cubed. And now just multiply and divide out the numbers, and you get something like 198.5 0.19 kilograms per cubic foot. Anybody have any questions about that? Okay. So that's pretty much all there is to unit conversions. The next thing I want to talk about is scientific notation. And I don't want to make this like a major point of emphasis in this class, but you do need to know how to do this. If you have a TI calculator, the answer to how to do this is probably just punching it into your calculator and it'll do the scientific notation for you, and that's fine with me. If you're comfortable with this, thinking about it your own way, that's perfectly fine with me too. But if you want an approach for it, this is one way that'll work. So the idea of scientific notation is that any number can be represented as a plus or minus, then one non-zero digit, then a decimal point, then a decimal, times 10 to some integer power. So for example, the number negative 3,490.6 can be written as negative 3.4906 times 10 to the third. And the number 0.000814 can be written as 8.14 times 10 to the minus fourth. And what's the benefit of this? One benefit is computer storage space, but we don't really care too much about that in this class. Another benefit is in physics, you deal with very small and very large numbers. Numbers where you would have to, so like for example, the mass of the Earth in kilograms is something like 6 times 10 to the 24th power, okay, kilograms. So if you were going to write out the mass of the Earth, you'd have to write a 6 and then count out 23 zeros. And if you miscount, I mean, that would take an annoying amount of time. And if you miscount on those zeros, you're not off by like some small amount. You're off by a factor of 10, you know? And so it's pretty hard to work with numbers that big in that way. The same thing with very small numbers, like the mass of an electron is something like, I'm blanking on what the number is, but let's say it's 9 times 10 to the minus 31st power. So you'd have to write a decimal point and then 30 zeros and then a 9. Obviously, it's just a place that would take a lot of time. It would take a lot of care so you don't miss any zeros. And then it would also be a hassle for the person to read. So, okay. In order to go back and forth between standard notation and scientific notation, you need to be able to go in both of those two directions. You need to be able to go from a standard number to scientific notation and scientific notation to a standard format. And like I said, if you're comfortable doing this already, then you can ignore what I'm saying. But I'm going to give you a set of steps that work for both of those two directions. Okay. So first, to go from standard notation to scientific notation. And as I do this, I'm going to follow along with an example, the number in red. So negative 541.6. Okay. So the first step is count the number of places. And I'm going to call this number that we're counting capital N. So count the number of places N that you'd have to move the decimal point left or right to have one leading, one non-zero leading digit. So in this example that's in red, we'd have to move the decimal point 2 places to the left. Okay, so N would be equal to 2. And we're moving it to the left. And then the second step and the last step is if you're moving the decimal point to the left, then you're going to be multiplying by times 10 to the positive N. And if you're moving the decimal point to the right, you're multiplying by times 10 to the negative N. In our example, we moved it 2 places to the left. So we have negative 5.416 times 10 to the positive 2. Any questions about that? Okay, the other thing we have to be able to do is to go from scientific notation to standard notation. And I'll use a different example for this one. So let's say for this one, the example number I'm going to use is 6.52 times 10 to the minus 4th. So the first step is the absolute value of the exponent. We're going to call it n. I said negative. Let's do this with a negative exponent for the example. Okay, so for this example, n is equal to just 4. We're just taking the absolute value. And then for the second step, if the exponent is positive, then move the decimal point n places to the right. And if the exponent is negative, move the decimal point n places to the left. Okay, so in our example, we know we're going to move the decimal point 4 places. The exponent was negative, so we're going to move it 4 places to the left. So you can think of this as we have the 6 and the 5 and the 2, and then everything else is, just place held by zeros as far as we need to go. So from scientific notation, we're starting here, and we're going to move 1, 2, 3, 4 places to the left. And so our number is, that should have all been in red. So our number is 0.000652. Are you with me on that? Okay. Let me give you a problem to work on. So let's say that we have, before I do this, there's one thing I want to point out. In these 2 directions that you have to go, the direction that the decimal place moves is opposite. So I want you to notice that. And the reason for that is you can think of these 2 steps. If you did them back to back, you'd just be undoing the steps you did. So if you move the decimal point to the left in the first step, you'd have to move it back to the right to get your starting answer again. Are you with me on that? So in the first one, positive exponents are associated with moving the decimal point to the left. In the second one, positive exponents are associated with moving it to the right. It's because of one has to undo the other one for this to work. Okay. So express negative 0.0000, so 4 zeros, 582 in scientific notation. So you can try doing it with the steps I just did, or if you're used to doing this, feel free to use the way that you're used to doing it. I didn't get that on video, so that's just for the, that's like a bonus for the people who are in class today. Okay, the last thing we have to talk about is unit prefixes. And so by this, I'm talking about centimeters, kilograms, the kilo, centa, milli, giga. Want to know something else from when I was a kid? The movie Back to the Future, where they make the flux capacitor to go back in time. They keep saying in that movie that that this motor or whatever has, I don't remember how much, 80 gigawatts of power or whatever, some number of gigawatts. They keep saying gigawatts. And that's giga, but back then, nobody knew how to say that because there was nothing in our daily life that was that went to that big an amount, But the computer age, we have, we use gigabytes and stuff all the time. So now we're totally familiar with that. But they were just looking at this random collection of letters basically. And they're I don't know, let's pronounce it giga. I think that's kind of funny. but giga is a prefix. Okay, so the main ones that we're going to see are micro, so this is going from smallest to largest. And micro is denoted with the Greek letter mu. And the Greek letter mu is the easiest one to remember because it looks kind of like an M and kind of like a U, and that's how you spell mu. And the meaning of micro is times 10 to the minus 6. And the next smallest one is milli. And that is represented with a lowercase m. And that means times 10 to the minus third. And the next one is centi. And that is a lowercase c. And that means times 10 to the minus second. And then next is kilo. That's a lowercase k. And that means times 10 to the positive third. And then the last one that I'm going to give you right now is mega. That's a capital M. And that means times 10 to the positive 6. And in order to work with these prefixes, you have to be able to do two things. You have to be able to go from something with a prefix to something without, and you have to be able to go from something without a prefix to something with. Okay, so I'm going to give it to you in 2 steps like that. And then if you need to go from something with a prefix to something with a different prefix, that just means you have to go through the intermediate step of no prefix. So we'll do an example like that. Okay, so first, if you're going from something with a prefix to something without a prefix, like you're trying to go from millimeters to millimeters, say. This is the easiest way to do it. It's just one single step. And all you do is replace the prefix with its mathematical meaning. Okay, so for example, if we want to go from 50 kilometers to figure out how many meters that is, then we'll go, 50 kilometers is equal to, and now I'm just going to replace that kilo with times 10 to the third, and then I'm done. So this is equal to 50 times 10 to the third meters, and that's all there is to it. Then, for formatting, if you're going to put this in scientific notation, this would be 5 times 10 to the fourth meters. Anybody? Yes?
Do you care which way we do it on the quiz or tests?
Nope. And then the second one is maybe like 2 steps. So if you're going from something with no prefix to something with a prefix, what you're going to do is use the definition of the prefix to find a conversion factor. And then do this change as a unit conversion. Okay, so for example, on this one, let's say we're starting with 100 grams and we want to convert that to micrograms. Okay, well, 1 microgram is equal to 1 times 10 to the minus 6 grams. I'm using the definition of micro there to come up with this equality. And so this gives us two possible conversion factors, 1 microgram over 1 times 10 to the minus 6 grams, or the reciprocal of that. And so now I'm going to do it like a unit conversion. I'm going to start with my given quantity, and I'm going to multiply it by the conversion factor that cancels grams. So I'll have 1 microgram in the numerator, 1 times 10 to the minus 6 grams in the denominator. The grams cancel. The units you're left with is micrograms. And now there's the matter of dealing with these exponents. You can just plug it into your calculator for one thing. But remember, the rules here are if you have, so these are the exponent rules. If you have something to the exponent m times something to the exponent n, that's equal to that same base to the power of m plus n. And if you're dividing, that's that same base to the power of m minus n. So 100 is 10 to the second. And then we're dividing it by 10 to the minus 6th, which means we have 2 minus negative 6, which means we have 1 times 10 to the positive 8 micrograms. So this is just over here as the exponent rules, just a reminder. But you also can just plug it into your calculator. I don't care that you know the cutest way to do exponent math. Anybody have any questions? Okay, let's do one more example problem. I'll give you time to work on it. I'm just gonna do it myself, I think. So this example I'm gonna do, I'm gonna go from one type of prefix to a different type of prefix, which means I'm gonna go from the prefix to no prefix and then back to a new prefix. That's the sort of the strategy. So the question is, convert 5 microseconds to milliseconds. So I'm going to go microseconds to seconds to milliseconds. The first step is easy. So we have 5 microseconds. And I'm just going to replace the micro with times 10 to the minus 6 because that's its mathematical definition in this list. So this is 5 times 10 to the minus 6 seconds. Okay. And then the second and last step is I'm going to go from seconds to milliseconds. So I'm going to use the equality that 1 millisecond, based on its definition from the list, is equal to 1 times 10 to the minus third seconds. And now I'm going to set it up as a unit conversion. 5 times 10 to the minus 6 seconds. I want to cancel the seconds, so I'm going to use the conversion factor that has seconds in the denominator to cancel this one. So I have 1 millisecond in the numerator, 1 times 10 to the minus third seconds in the denominator. The seconds cancel, and we get an answer of 5 times 10 to the minus 6 minus a negative 3. So minus 6 plus 3. So 10 to the minus third milliseconds. Anybody have any questions about that? Okay, well, that's all I want to talk about today. Anybody have any overall questions before you go? So by tonight sometime, there will be an assignment on D2L, so just look in the announcements, and then that will be due by next Tuesday at midnight. Okay, bye, have a nice weekend. Oh, remember, no school on Monday, Labor Day. So yeah, I don't know if the school will be open, but if you get here, it might be locked. There definitely won't be any classes.